Welcome to the Here's a Summer of Testing. This is a collection of tutorials focusing only on testing and is a separate series to the usual Here's a Seminar series. Hello and welcome to today's Here's a Summer of Testing seminar and tutorial. My name is Jakob Fritz from the Forschungszentrum Jülich and I want to talk about testing in Python. So, I want to start with the parts linting and formatting. Then I will talk about how to do unit tests using PyTest, how to check your test coverage and why it's important to know it. Then I will go into an advanced topic of property-based testing, what it is and where it might help you. And I want to give you some conclusions and some links for further reading. So, let's start with the linting and formatting. It's an easy way to check for syntactic correctness. It does not check, however, for semantic correctness, so it does not check whether your code returns correct results or not. Popular examples for it are Flake8, PyLint or Rough. I will use Rough in this tutorial. What does it do? Well, it finds, for example, missing brackets, unused imports, unused variables, if your lines are too long, and such things and much more. In this tutorial, I want to give you an example in the file linting.py in the directory of here's a SRT, which I will use throughout the whole tutorial. In there, I first import a package, which I don't need, and then I have a function, which is very exciting and prints two outputs. The first line is rather short, the second line is quite long. So when I run the linting, which I can do by simply running rough with a dot, so it lints the local directory, it returns some errors, 2 in this case. So it first returns that pandas is imported but not used, so we don't need to import it, and then it returns that one line is too long. In this case, it has 112 characters instead of the 88 that rough wants per line at most. And then we know where to fix our style. So when we manually reformat it, we don't need to import pandas, so I commented it out. You could also remove it. And I added a line break in the second print statement to have shorter lines. If we now run rough again, we see it doesn't return anything. And as often with terminal commands, if it doesn't return anything, it's a good sign. So, after linting, I want to go into auto-formatting. It is a way to have a consistent style of code, both across developers, so if you work in a team, but also across time. So even if you work alone, I can recommend to use some formatting, to use an auto-formatter, as your code style might change over time, and therefore using this formatter keeps a consistent style. And it also increases the readability of the code. One popular example for this is Black, and I will use it in this tutorial. So again, we use the linting.py file in the state as it was prior to the manual corrections, and we now don't use rough, but we use Black. So when we run Black, it says, well, I did do some reformatting on one specific file, and now all is done, all is nice. So one file reformatted, no files left unchanged, as there was only the single file. So let's have a look what Black changed. After the automatic reformatting by Black, it looks like that. And if we now run it again, it says everything is done, one file left unchanged. What happened previously was that we have a second empty line between the import statement and the definition of the function, and it also added line breaks in the second print statement. However, it did not break the single long string. It just shortened the line by splitting up the brackets of the print statement to have it a little shorter. So, as you might have guessed, it's a good idea to combine those two, as both have their strengths and weaknesses. For example, Black did not tell you about the unused import of pandas. Linting also finds these unused packages as just mentioned, whereas BLAC, for example, as automatic auto formatting, takes easier care of line length. So my current approach is to write code, then run first BLAC and then directly rough, then take care of errors thrown or raised by rough, and then run both of them again, and hopefully BLAC doesn't change anything and rough doesn't complain about anything and therefore doesn't return anything. So when combining these two things, the linter and the auto formatter, we can see the effect. Here again I showed you the state of the file prior to the automatic and manual reformatting. Then we run BLAC, then we run rough. So BLAC first reformats it, rough still finds two things. Again, the imported but unused pandas, and although BLAC reformatted it, the line is still quite long. So now we do some manual formatting. So we comment out the import and we add a line break in it. Then we run BLAC and we run rough, and both are happy and satisfied. And now the code is much more readable and nicer and easier to understand. I want to go on with unit tests and how to do them, in this case with PyTest. So after the linting, I want to go on with the unit tests, and they check for semantic correctness. So they don't check on whether your code is nicely formatted, but they check on whether your code returns correct results. They do not check, however, whether your code runs faster than before or slower. An example often seen in the context of Python code is the package PyTest. Compared to linting and auto-formatting, you need to specify the tests yourself, as they are specific to your code, and therefore you need to do them yourselves. You can't just run as rough or BLAC, because you need knowledge of what your code shall actually do. For this, you put the tests in a separate directory to have them split to your code of your package, and you name the files with either beginning with test underscore or ending with test underscore, so test underscore whatever.py or whatever underscore test.py. You need to prefix the function in these files with the keyword test, and the init files are needed but can be empty. So the recommended layout could be like the following. This is taken from the PyTest website. So you have a setup.py file, you have two directories, one for your package with an empty init file in it, and whatever files you need for your code, in this case app and helper. And then you have a directory, a folder called tests, with again an empty init file, please remember to have it, and two more files. In this case, they both start with test underscore. Those two files, as you could easily guess from the name, test the other files app and helper, and therefore it is easy to find where to find tests or where to also add them. But let's look into those. In my tutorial, I added a function called isEven in a new file, example functions.py. This isEven function gets a number and it wants to check whether this number is even or if it is odd. So if it is even, the modulo of the number using 2 should be 0. So therefore it calculates the modulo of the number, and if that is 0, it returns true, otherwise it returns false. As we now have written code, we want to check whether it works as expected. And for this, we create a file testeven.py in a separate directory called test. In there, we import our example functions and have a new function called test underscore, and then I chose the name isEven. I don't need to give it any arguments, but we just call the function example functions.isEven with an argument of 4, store it in a variable, and then use the assert keyword, which is a reserved keyword in Python, with that variable. Then again, we repeat it with an input variable of 5. These two assert variables or assert keywords using the variables in this case are keywords in Python, and they need to evaluate to true. So result 4 needs to be true for this to succeed, because after the assert statement, whatever follows needs to be evaluated to true. It could also be a comparison, or you can concatenate stuff, but it needs to be evaluated to true in the end. The second assert statement needs to also evaluate to true, as we added a not there. Result 5, the content of the variable result 5 needs to be false, so that the whole thing again is true. And then we are done. We defined a function, we wrote a simple test for it, testing for 2 input arguments, and now we can run it. For this, we need to install our newly developed function, our newly developed package, with pip install -e dot to locally install the new package. In my case, here's a SOT, and we install it with the -e, so in editable mode, to not install it every time we want to test it, but it just keeps staying up to date. Then we can run PyTest. And we do it with just calling PyTest and a dot to test in the local directory. Then PyTest automatically finds the directory called test, and in there all Python files with a test in the beginning or at the end, and in those files all functions that start with test. In our case, it collected one item, and it found this one item in the directory test, in the file testeven.py, and in there it found one function, and you see this one single dot. That means the one test ran and succeeded, and it all worked in way under a second. So we can also check not only if everything worked as expected, but if we have code that shall raise errors in certain occasions, we can also check if those errors are raised correctly. So in this case, I added another function called isEvenAdvanced. It also takes a number, and the first thing it does is it checks whether the input variable is of the type integer. If not, a type error is raised with a string expected in integer. If the input variable is an integer, it's just forwarded using the isEven function, and the result of the isEven function is then returned. So it's just basically a simple wrapper testing for the type of the input variable. We could also have it in our original function. I decided to have another one because it's easier to show you here. In the testeven.py file, I added a second test. That one is test isEvenAdvanced, and to check whether these errors are properly raised, I need to import PyTest as a package. Therefore, I added a second import statement at the top of the file, and then in the file I can check whether the type error is properly raised. This is done by using the with keyword. So when calling the example function isEvenAdvanced with a variable that is not an integer, because in this case it is a string, we expect the function to raise an error of type error. And this is repeated if we give it a float instead of an integer. And then we have these two asserts because we want to check whether this forwarding properly works. So we call the isEvenAdvanced with a value of 4 as an integer and a value of 5 as in our previous test. And with this we can check whether the error is raised. So if we call it and the type error, if we call it with a string for example and the type error is raised, everything is fine. If we call it and no error is raised, PyTest will have this test as failed because we expect a type error to be raised. And if any other type of error is raised, the test also fails because we expected this specific type of error to be raised. So we now call it, again, PyTest dot, and then we see a second dot after the file name. That means a second test ran and it succeeded. So what do we see if a test actually fails? Because now they succeeded, which is nice, but often tests fail, at least in the first place. Then we do whatever correction and then they hopefully succeed. So I added another test and I assume that this test will fail because I assert that the number 5 is even, which it is not. And therefore this assert should fail. So if we run it now, we see 2 dots, because in this file 2 tests ran and succeeded, and instead of a third dot we see an F. And this F means 1 test failed. And down below you see failures. And this is not all of the output, but there is more. So the upper part I just showed you, now it gives you some more details on the failed test. So it says in this test failing there is an assert statement, example func is even 5, which is false, and assert false raises an error, and it gives you even more replies, even more information on this function. And at the bottom line it gives you a short test summary, which test failed, and the summary that 1 test failed, 2 succeeded, and overall it took 0.03 seconds. So what do we do if we now have this test and it fails, and we say like, yeah, I do know it fails and I will care about it later, but I want to go on first to keep to take care of other things first. So we can mark this test to be skipped, so it won't be executed. And we can do it after importing PyTest again. Then we can use a so-called decorator with the @ symbol above the definition of the function. And here we have this PyTest mark skip. And when we now run PyTest again, it looks like that. We have in this function 2 dots because 2 tests ran and succeeded, and instead of a third dot or an F, we have an S. And this means that 1 test is skipped. So after this I want to go into some further aspects of testing. There are so-called integration tests. These test not whether a single function tests as it should, but whether multiple functions work together as they should, whether the interaction of those is correct. And there are system tests or end-to-end tests, and they not only test some few functions and the interaction of them, but whole systems, or like from one end to the software to the other, so like whole walkthrough. Both are normally conducted when unit tests are done and finished successfully, and both are outside of the scope as we want to get started with unit tests and with testing in general. And with this I want to go on to the next part, test coverage. I just said that you can use integration tests, system tests, to test whether multiple functions work together as they should, and normally those are done once the unit test succeeded and once your code is tested. But how do you know if your code really is fully tested? In our case it is rather simple because we wrote only very few functions, so it's easy to know whether we tested those or not. But if your code is larger, it's not that easy. And we want our code to be tested because all untested code could potentially be wrong without us noticing. And we can use the package coverage for it. And we install it just as pytest -conf, or do it in the environment file if we use conda or mamba. So to repeat, we had the pytest with a dot. We get the reply of 2 functions tested and succeeded, 1 is skipped. If we now add a keyword argument to the pytest, we can get more information. We use the --conf and then followed by the directory. And this case, the code is placed in the directory here's a SOT. And if we run it with this additional command line argument, we get a second part below the test even with the 2 dots and the S. We get some information on the Python version and the used platform, and we get some information on which code actually was executed. So in the here's a SOT, we have an init file without any statements and no misses. So we could say we have 100% coverage. We have another function, example funcs, with 9 statements overall in all functions and 0 misses, so we have 100% coverage, which is nice. Then we have a function linting.py, which I used in the previous part, that has 3 statements and 3 misses, so we have 0 coverage. And overall we have 12 statements, 3 misses, leading to 75% coverage. With this, these statements mean actual lines of code. So nevertheless, please do add comments to your code. These are not counted into these statements, so they don't bring down your coverage, but make your code easier to understand. These statements are not lines of the file, but actual lines of code. And at the very bottom, we again get our information: 2 passed, 1 is skipped in some duration. Now we know that 75% of our overall code is tested, that we missed 3 out of 3 statements in the linting.py file. If it's 3 out of 3, it's rather easy to know which one, because it's just all of them. But if it's, say, you missed 10 lines out of 120 statements, it's not too trivial to know what tests to add to actually test those lines. And for this we can add another command line argument. If we add the COF report with the value term missing, we get an additional column called missing. And in this case, it tells us that the lines 9 to 11 are untested. Again, in this case, it's trivial because there are only 3 statements and we missed all of them. But if you have large files, this is really helpful to know which parts of the code were actually executed and which were not. As you can see, the time slightly goes up because the PyTest and the coverage need to do additional logging to actually know which lines of code were tested. So please keep that in mind if you want to do benchmarking, if you want to use the duration of tests for any more information, to only compare when you have those options disabled or enabled in all cases. But if you actually want to do continuous benchmarking, do it differently without the coverage estimation. And with this, I want to go onto property-based testing. So previously, we specified exact input data and specific output data. So the asserts could look like something: we assert that y, which is predefined, is exactly the return value of a function we want to test given the input value of x. And if the function returns the same value as we assumed before, and we stored in the value y, the assert is true and we are all happy. So we risk of missing edge cases, or we do quite repetitive work because we conduct similar tests with slightly different input data many times. And there's a package called Hypothesis that we can use for it. Again, it's easily installed with the name Hypothesis. And to show you it, I added another file called random increase. And for this file, in this file, I added a function increase number. And the function increases a given number by an integer between 1 and 10, and then returns the sum of it. To actually test it, I added another file called test_randomincrease.py, and in there I imported Hypothesis. And from there I imported some hypothesis strategies, and I will tell you what those are in a moment. And I imported the given and the example from Hypothesis. In the lower part you can see that I defined a function test random increase, and this function now takes an input variable compared to the other testing functions which did not. And for this input variable number we define input data, and we do it with the given decorator. In there we define some function, and this function from the strategies part returns and generates arbitrary integers. These strategy integers creates those integers, and those are passed into the test function as number. We can also specify examples that are always tested. So we always want to test with an input number of 5. In this testing function, we call our developed function increase number and store the result. In the result, we assert that the value of the result is of type integer, and we assert that it is really larger than the input number that we passed into. So if we now run the PyTest, it looks like the following. We have the test even with 2 passed functions with 2 passed tests and 1 skipped one, and we have another line, test random increase, with a single dot after it. Now also the percentages on the right changed, as after finishing the first file it had 75% of all tests, so 3 out of 4. And the summary is 3 passed, 1 skipped, and the duration went up again because hypothesis tests multiple cases because it generates input data and tests for those cases. Function succeeded and we are happy. Now we want to add more things to it. So we now don't only want to increase integers, but we also want to increase floats. And for this, I created another function to test it. So I left the previous one unchanged and added another one. In this case, I added from the strategies the function one-off. So to that we pass a list of strategies and it just picks one by chance. And in this list we have the function returning arbitrary integers, and we now also have a function returning arbitrary floats. And furthermore, we also make sure that at least this one specific float, 4.5, is always tested. And now, because we pass in floats, the result might not only be an integer, but it also might be a float, and therefore we adapted this isInstance method, this check, to accept both ints and floats. And yeah, looks good, so we just test it. And it failed. So we see that we have, in the test random increase, we have 2 functions. The first test succeeded, you see the dot, and the second one failed. Why? Well, we can have again a look into this failure section. And in there it tells us that it failed for a case where number equals 7 point whatever to the power of 16. So we now know that if we throw in very large floats, the function won't work as we expected. So we get the assert that the result is not larger than the number, because we tested whether it is larger and the assert was false. So they don't compare larger to one another. Well, seems like we found an edge case for it. If we give it very large floats, the function won't work as expected. So with this knowledge, we might go back to developing our function to fix that, or if we say we cannot do it, well, at least specify it in the documentation that other users know of this behavior, because they might not expect it. And because now we know that this happens, we specify our test to exclude these edge cases. And this is done by adding keyword arguments to the strategy returning floats. In this case, we specified an upper and a lower limit. So the float shall not be smaller, shall not be lower than -1 to the power of 15, and shall not be larger than 1 to the power of 15. And after we specified these floats, you can see that all tests succeeded. So in the first file, 2 succeeded, 1 was skipped, and the second file we see the 2 dots instead of dot and an F, so both tests succeeded. And with this, I want to conclude the part of the property-based testing. It is used to check the properties of the data rather than the specific values of the data. So you can check whether your input and your output is of a given type, if one is larger than the other, and so on. So, as you might already expect, it is great for refactoring code, because there you have 2 functions that shall return the same result for basically any input. And therefore it's easy to test and throw many different examples at those 2 functions and check whether both functions behave the same. You can also create many different types of data for input. So it's not limited to the integers and floats that I just used and showed you, but you can also create many more and even composite ones if you want to have very complex input data examples. Please see it as an addition rather than a replacement for testing with specific inputs and outputs. And last, some recommendation: you can add the directory .hypothesis to your gitignore file, as hypothesis stores the examples there, and otherwise they are added to your Git repository if you don't exclude this directory with a gitignore. So I want to conclude today's tutorial. I showed you with linting and formatting that they can help you to find syntactic errors and correct maybe bad style. They also help you or even automatically fix those, and they are very easy to add as they are not specific to the task that your code actually does. So please just add them to your continuous integration to check on every push to the server. Examples for it are Black and Rough. I used those 2. More examples are PyLint and Flake8. I talked to you about unit tests and used PyTest for it. Unit test is used to find where your code acts wrong. So you find semantic errors, where you expect some function to return a value, whether it's even or not, and if that function works as it should. The tests need to be written specifically for your code because they depend on what your code actually wants or plans to do. And therefore there is no one-size-fits-all solution, but you need to do those tests yourself. The example and the framework I used for it are PyTest. I furthermore talked briefly about the integration tests and end-to-end tests, and they are used to check whether functions interact as expected, work together as they should. I showed you the test coverage and why it is important to detect where untested code actually is, and therefore it helps to decide on where to add additional tests to check all your code. And lastly, I talked to you about property-based testing. It's a more abstract concept because it's not testing for specific values, but it's more testing for types and properties of your input and output data. It helps to find edge cases, as you just saw, and it's an addition rather than replacement for the regular tests where you specified the input and the output. Those tests are sometimes called golden record tests. And lastly, I want to give you some more further reading. You can have a look into the websites of Rough and Flake8, 2 popular linters, to Black, which are used as auto-formatting tool. I linked you also the getting started and some good practices from PyTest, as well as the package coverage, which I used in combination with PyTest. And furthermore, I linked you the hypothesis package, which I used for the property-based testing. The last link points to the repository where I put all the files that I showed you today if you want to have a look at them. And with this, I want to thank you for your attention. I wish you a good day. Goodbye. Thank you for watching this tutorial. Please check out the slides on Zenodo, linked below, and see you next time.